Dope.
I would know. You left before I took it off.
Hooray, there it goes. How many of you have taken the exam? How many of you are normal and are going to take it today? That's what I figured. So those of you who have taken the exam, anything weird going on with this one? No questions that are missing questions and only have the answers? No scores of 0%? Every answer is wrong.
How long is it taking people to do?
Yeah, not even an hour.
Yeah, 50 multiple choice, and then the essay question. Don't forget to answer the essay question. It should just fit in the back, in that blank space on the back of the scan. Yeah, no, you're not going to need a blue book unless you write big, in which case you might want to bring a blue book, but it should fit in that. So that's about what we're expecting people to do.
How many points is the essay question?
1 million. I don't remember exactly.
50.
50. Yeah. So the multiple choice, 50 questions worth 2 points each. So that's 100, and then the essay is 50 points. So total thing, 150. Why?
Well, it's just a lot of weight on the essay question.
Well, I gave you the essay questions like a week ago, right? More than a week ago. They should be really good answers and succinct to fit in that space. Okay, so this one is going well. So I've got 3 classes, and I mean, like all of your other professors, I'm giving exams in all 3 classes. In one of the classes, one of the questions is gone, so it's just the answers. So it was just formatted badly. It turns out that the question was on one page and it got dropped off, but the answers remained. And then in my other one, but it could be worse. My other class, I got an email, frantic email on Monday night. Somebody came out and said, I got a 2% on the exam. What's going on? It turns out that she had got so the key apparently was blank. So the one that she had gotten right was the one that she had skipped. And so it was scored as being right, and then all the other ones that she had answered were all marked wrong. Yeah, that's got to be an awful feeling. 2? I only got 1 right. I mean, that's significantly worse than chance, right? Yeah, no, I felt really bad for her. I'm like, oh, dude. I assume that she figured, oh, that's got to be a mistake. Huh?
Do you have any extra markers to use?
Go ahead and take it.
Thank you.
It probably doesn't work anyhow, does it? All right, so let's talk about size perception. So how do we know if we're looking at something that's tiny and really close or something that's big and really far away? So how do we know how big objects appear? So how big an object seems to be depends mainly on 2 things. The visual angle and the apparent distance. So visual angle refers to basically the room that it takes up on your retina. So how much angle is occupied by the object? So if it occupies a lot of the visual angle, then it's going to be perceived as being closer, whereas something that occupies less of the visual angle is going to be perceived as being farther away. Now, under these circumstances, though, if you've got something small that's closer and something larger that's farther away, they're both going to occupy the same amount of visual angle. So visual angle isn't everything. Here's another example of visual angle. So you can see the same size person at different distances. You can see that the angle is smaller here than it is here. We're not going to worry about how you actually measure visual angle. So your thumb held out at arm's length is about 2 degrees of visual angle. So you can actually measure this and quantify how much space do these things occupy. So how do we figure out? So you've got the visual angle. That's immediately obvious, right? That's just what's present on your retina. But then, is that everything? Is that all that you need? Obviously not, because we get fooled all the time, right? Of things that look really big, but are just really close. And this was demonstrated by an experiment by two folks named Holloway and Boring, This is probably one of the worst names in all of science. The boring experiment, in which they had subjects standing at the intersection of two hallways. So you can look down one hallway and look down the other hallway, and you have down one hallway you have a test circle. No, down one hallway you have the comparison circle. So it's always 10 feet away, and your job is for the test circle to decide if it is how far away it is. Now the test circles can be larger or smaller in size, so you can vary both the size of the object and its distance. So you can do things like have your comparison circle here, so it looks like this. And this is all dark, so you can't see the hallway around it. All you can see are these glowing discs, right? So how do you judge whether this is larger than something that's close, but still occupies the same amount of visual angle, or something that's farther away and also occupies the same amount of visual angle? Well, how do you think people do at this? Are they able to tell the difference between these and this? Sarah?
I think you'd need reference clues around the light. Like if the light was the only thing that was there, you couldn't tell if it was farther away or not.
Right, and that's exactly the case. So on each trial, if it's all done completely in the dark, if you don't have any reference clues, if you don't have any clues to how far away things are, like if you don't have anything to compare it against, then Sarah's absolutely right. You can't tell the difference between these things. So these are the predictions. I don't want the predictions. I want the data. So in conditions 1 and 2, if you've got depth cues, so if you've got the lights on and you have the ability to tell how far away things are, then you can correctly estimate the size of the objects. So if you have depth cues, then judgments of size were based on the actual physical size of the object. If you take away the depth cues, judgments of size are based on the visual angle, and so you're much worse. You're much closer to basically chance at determining the size. So if you have, so this is near and far, if you have cues to depth, then you're pretty good at judging the visual size. But if we increase the visual size and also increase the distance so that the visual angle stays the same, and if we take away the depth cues, then you're pretty bad at it. You're basically just judging it on visual angle, which isn't going to give you that much information. Justin?
What kind of depth cues did they use? Like,
I'm trying to remember. I think that they just...
in both hallways, or?
I think that they just, flipped on the light so that you could see, the bricks in the walls or the tiles or something like that. And in these, you just take away the lighting cues. You just have the luminous discs that are taking up a certain amount of visual angle. Oh, I've got it here in my notes because I knew that I was going to forget it. So condition 1 was you have both eyes and the lights are on and there's nothing obscuring your view. Condition 2 is you've got one eye closed, the lights are on and it's obscuring your view. So it turns out you don't need both eyes to tell the difference. Condition 3 was you're looking through a peephole. So all that you can see through the peephole is the disc. You can't see any of the other information around it. And then condition 4 was drapes. So you have basically you're taking away all of the walls and everything. All right. So how can visual angle explain astronomical phenomena, such as an eclipse, for example? So the sun is how big? Really big. How far away is the sun? Really far away. How big is the moon? Also really big. But not nearly as big as the sun. Right. So how do solar eclipses work, if that's the case? Well, it turns out that the apparent size of the sun and the apparent size of the moon is approximately equal. The moon and the sun both take up about half a degree of visual angle. Although the diameter of the moon is 2,200 miles and the diameter of the sun is 865,000 miles, the moon is also much closer. 245,000 miles away, whereas the sun is 93 million miles away. So the apparent size, the amount of visual angle between the two is approximately equal. If it were anything other than this, then either the sun would be completely obscured and you wouldn't get the aurora around it, or the moon would not block out the sun at all if it was smaller or farther away. How cool is that it just happens to be exactly the right size? Or maybe it doesn't. I don't think that I care about this, to tell you the truth, because I want to talk about something else. I want to talk about illusions, actually. All right, so this is the famous Müller-Lyer illusion. Now, can we use any of the principles that we've talked about to explain the Müller-Lyer illusion? So I know that the one on the left, the vertical line, from the arrows on the left and the whatever that is on the right, are the same. Even though I know that, does it appear the same? No. So what's going on?
Could be part of the common region, because it almost looks like the one on the left is like closed in, so you might assume that those points are closer together, since the other is opened up. You see it as like different areas.
Okay, so maybe this whole, I've left my pointer over here. So maybe you just have a gestalt. I know it works, it was just working. All right, so maybe you have a gestalt perception of the one on the right and the whole common region. So if you were to color in the whole thing, then you would color in more on the right than on, oh, now it's working. So you color in all the way up here for this one and down here, whereas this one is different. Okay. But why? What about these? So the obvious difference is the arrow things. What about these arrows tells us that this is bigger than this?
Looks like the one on the left is kind of like being pushed in by the two arrows on the side, whereas the one on the right looks like it's being drawn out, like more open.
Okay, yeah. So if you were to take these lines and extend them out, I'm like, dude, it's still in my marker. So you've got the one on the, I have to be careful about it. All right. So if you were to take these lines and extend them out and say this is the corner of a wall, for example, or this one also being the corner of a wall, which one is closer? One on the left is sort of coming out toward you, right? So I think I've got an example of this. Do I? Here we go. So this is sort of like the Müller-Lyer illusion, right? This is not exactly right because you could take a better picture or Photoshop this one so that it actually worked out to be right. But it sort of illustrates the point, right? So if you've got two lines that are coming in like that, in this angle, then, as in the one on the right, then that indicates that that is a wall that's receding away from you, right? Whereas these angles indicate that the wall is coming out toward you. So maybe it's our size perception that's being tricked here. So maybe we're interpreting this one as being closer, or this one is coming out towards us, and maybe being a little bit farther away, whereas this one is closer to us and going away from us. And so that's why they appear the same size. Does that make any sense? No? Sort of-ish.
Sorry, if the closed one was closer, wouldn't you see that one as larger? So if you had one coming out at you and one
Oh, I think I said it backwards. Yeah, so if this one is closer than this one, then you should see this one is larger than that one. Is that what you're saying?
Yeah, that would be my guess. But if
Sarah says no. How come?
Okay, because if you assume the other one's farther away, then you just assume that if they were at the same, if they were right next to each other, the farther one is longer.
Does that make sense? So if this one is farther away and it takes up the same amount of visual angle, then what does your visual system do to take that into account? It assumes that this one is farther away and larger. That's why it looks like it's the same size as this one. So it's not that the physical stimulus is that this one is larger than that one. It's that the physical stimulus is that they're the same size. But the other cues to depth indicate that this one is farther away than this one. And so you interpret that as, well, it's the same size, but it's farther away, and so it must be, in reality, larger. Does that make sense?
Is it weird then that I see the one on the left as larger? Like for me, it's the arrows they're like drawing out the line longer.
Yes, it is. You're abnormal. No, actually, that is kind of unusual that you would see the one on the left is larger. Typically, the perception is the other way around, but what you're doing makes sense, right? You're perceptually organizing that as being dynamic and being stretched out, whereas this one is maybe being dynamic and being squashed in. So usually people interpret this as a static image, and maybe like the corner of a wall. The walls don't move, the walls don't come up and out. But if you're interpreting it that way, then that top-down processing is going to influence your perception of it. So it's not weird that you see it. It's just people normally perceive these as being static, but if you're perceiving them as being dynamic, then that would make sense. Other questions? All right. Yeah, this is more explanation of what we just did. I don't want to talk about all of that stuff because we basically went over all of that stuff. All right, the Ponzo illusion. Ponzo illusion is actually much more powerful and much more consistent. So the Ponzo illusion takes advantage of the fact that parallel lines tend to converge in the distance. So what you can do, let me show you this rather than trying to explain it, is you can take two boxes that are exactly the same size, superimpose them on an image, and that one looks much bigger, doesn't it? Is it actually the same size? So if you draw a straight line from here down and from here down, yeah, they're exactly the same size. So even if I tell you they're the same size, even if you hold up your book and figure out, okay, that's the same size as that, does it even look remotely the same size? No, it's a very powerful illusion. It's a very powerful cue. So here again, you're taking this visual information. It subtends the same amount of visual angle at the top and at the bottom, and your visual system is fixing that and saying, okay, but that one is farther away. And so if it appears to be the same size, it must be much larger in order for that to happen. Here's another illusion that takes advantage of parallel lines converging in the distance. So I've got this picture on this side, same picture on the other side, so everybody sees that these are the exact same picture. I haven't done anything squirrely with them. Do they appear that they're going in the same direction? Why not? So it's the same picture in both cases, but the one on the right appears to be going in a much different direction than the one on the left. The angle appears to be much different. Any ideas what's going on here?
It reminds me of those pictures when the eyes follow you. Like the lines, as I move my line of sight, the lines are still coming from kind of the center. Or like, and maybe it's because I'm seeing it from an angle the way I'm perceiving this explanation, but like that one looks like it's coming from here in my visual field, and that one's like this one. I don't know if that's really clear.
Yeah, no, from this angle I get the same thing, that this one is going from farther over in the left, right? And then the one on the right is more toward the center. But they're the same. Justin?
Because they're right next to each other, so you have lines coming, and then it goes against almost perpendicular, so you assume the one on the right is going more forward than the picture on the left.
Yeah, it is. It does depend on how I've arranged them side by side. So if I were to stack them one on top of the other, then the effect would go away. They would look like they're going in the same direction.
What if you pull them apart? Would it still?
Ooh, that's a good question. I don't know.
I think it would still, as long as you can see that the inside or the apparent inside lines are moving,
Yeah.
then it would still stay true.
You want to mess with it and see? All right, so it does depend on their relationship to one another, and it depends on all the depth cues that you're getting out of this, right? So once again, it's not just the absolute angle of these things, it's all the rest of this. Because if I just had two lines on the screen that were the same orientation as the two rails, then I think that you'd be able to say, yes, those are definitely the same orientation. So imagine all the rest of this going away and just having rail 1 and rail 2 and lines that correspond to that. I think that you'd be able to see that those are the same angles. It's just when you have all the rest of this stuff, all the rest of the cues to depth, that you're sort of fooled by that.
And when I look at just this corresponding rail, I can tell if they're parallel.
Right, yeah. So if you ignore all the rest of this and just focus on that one rail, then yeah, it looks the same. Otherwise, you're fooled.
I think it's a depth perception thing too, because your brain is always trying to find the one vanishing point where it's going back to. But in this case, if we did continue this line into this picture, it would intersect at an angle that would ruin that reality.
Right, so you're sort of interpreting that's the vanishing point, or that's the vanishing point. So either way, one of them is right and the other one is not. So you can only have one. So if I stack them up on top of each other, then the vanishing points are going to line up. So that's fine, and that doesn't matter. But if they're next to each other, then the vanishing points are going to conflict with one another, and the illusion is going to occur. All right, the Ames Room. I've got a better video of the Ames Room. This one works, though. I'm not sure what it has to do with Quaker Oats, to tell you the truth.
It's great. There's a White Stripes video edited it.
Ooh, that would be actually a lot more fun.
It's kind of cool.
Jack White in here.
This is really weird.
So what's the trick here? How do we get guy 1 and guy 2 to grow and shrink, respectively?
There's a step on the ground.
It kind of looks like it. The ground is flat, actually.
It's probably
Well,
slow.
it's not. It's sloped. So it's smooth, but it's not.
This one has.
Yeah, he's climbing a slope. He's not actually going upstairs, but he is climbing a slope.
And in the back, the window's just way bigger than it would be.
I think, yeah, it's a lot of relative size.
Yeah.
So it's got one next to like the little window on the right, but a giant window on the left.
Right, exactly.
And then there's the probably the horizon effect is in there.
Yeah. So it takes advantage of a whole lot of stuff. So this is, if you were looking at the top of the Ames Room, from the top down, this is the shape of the room. So the window in the back is actually much larger. So the shape from the top down looks like this, and if you look at it straight on, the back wall is actually much taller in the back as well. So it's all relative size, right? And it's all taking advantage of this idea that if you have the same amount of visual angle for the near corner of the back wall and the far corner of the back wall, then your visual system interprets that as being as lining up. So this is the actual position of person B. This is the actual position of person A, but their apparent position, because you've sort of rigged everything to appear like it's all parallel, is that, well, this person, their visual angle has gotten much smaller, and so that person has also gotten much smaller. And it all depends on viewing it from this exact point. So you have to look at these things through a peephole, because it's all relative to that viewing spot. If you move over even slightly, then you can see, oh wait, that wall gets bigger as it goes farther back, or that floor is sloped. It all depends on where you're viewing it from. I've got a good demonstration of this. Again, back to my visual illusions folder. Ah, I found it right away. So this is the same sort of thing. So this is not a filter superimposed on this image. This is actually painted on this hallway. And if you view it from exactly the right spot in the middle of the hallway, it looks like checkers. But if you move slightly to the left, this is the same scene. It's really clever.
Where is that?
I don't know where this is, actually. This is the same sort of thing with those sidewalk illusions, where it looks like the sidewalk has fallen away, and you know, if you walk out onto it, you're going to fall in a big hole. If you view it from the side, then it looks like everything is sort of stretched out, but if you look at it from exactly the right spot, then the illusion works. This is the same sort of idea. So this is the Ames room. So the observer thinks that the room is normal, because why would you think that this is a screwy room that's got a big trapezoid wall in the back? So the people would be at the same distance. So you assume the people are at the same distance. You assume that the wall is perpendicular to you. One of the people has a smaller visual angle. The perceptual distance you assume is actually, the perceived distance is the same. And so you perceive the person as being smaller. All right. Does everybody know what the moon illusion is? So when you see the moon coming up over the mountain, here in Provo, it looks really, really big. But then if you see the moon straight up above you, it doesn't look quite so big. So the moon on the horizon looks much larger than the moon straight up in the sky.
Isn't that because like the atmosphere distorts it?
That's one idea. Doesn't explain all of it. So you would, if it's going to distort it, it's going to distort the roundness of it as well, right? But it still appears to be round on the horizon. So it's not magnifying it, and it's not really distorting. So if it was distorted, it would probably make it look sort of oblong that way. But we don't. So, and if you take an actual measurement of the visual angle, so take a picture of it here, take a picture of it there, the visual angle is still the same. So it's not actually being distorted.
When we see the moon like on the horizon next to the mountains, we have that comparative aspect of it, whereas up in the sky it's just a bunch of nothing, and the sky's enormous.
Right, exactly. So you've got no idea how big the sky is. It's like space. Space is, what's the line from Doug Adams? The Hitchhiker's Guide to the Galaxy.
It's really big.
Yeah, that's the idea. Is that we've got no idea how big it is. Mind-bogglingly big. So this is what's known as the angular size contrast theory. So when the moon appears next to the mountains, you know about how big the mountains are, right? Mountains are huge. And they appear yay big, and so the moon, well, that looks as big as the mountains, and I know that it's behind the mountains because it just came up from behind the mountains, and so, wow, that's really big. But straight up above you, do you have anything to compare it to? No. It's still the same angular size. It takes up the same amount of your retinas, but you don't have anything to compare it against because we sort of assume that the sky is kind of flattened out. Or at least visually, it doesn't appear to be as big. So we have sort of this flattened heavens, that it's not really a true circle going around here, that it appears somewhat different. So the moon on the horizon and the moon straight up above, we perceive that as being different. So here's an example of the moon illusion. So with the mountain to compare against, it looks huge. I think this is Photoshop trickery. You want to see it again?
Yes.
It is pretty good, huh? Now that you know the trick. Is that the car from Ferris Bueller's Day Off? It might be. These are pretty common. So this is pretty easy to do. You just have to line everything up exactly. So this guy appears to be a giant and she appears to be tiny.
Lord of the Rings uses that a lot.
Oh, yeah.
Where they made the hobbits look so small.
Yeah, exactly. So that's why it looks a little bit weird sometimes. The sight lines aren't quite right on. So they're supposed to be talking to each other, but one person is over here and one person is right here. And they're both looking past each other. Forced perspective is what that's called. I think this is pretty clever. Also clever. So I found all of these online. I didn't search for screwball MTC pictures. I just happened to find it. Yeah, he's lighting a cigarette off the sun. This one took me a minute to figure out what was going on.
Oh my gosh.
This was actually a public, sort of a public awareness campaign to get people to pay attention and freak them out, I guess. You're driving along and then all of a sudden you see a kid in the middle. Oh, wait.
A magically growing
A
child.
magically growing child in the middle of the street. Oh, I've shown you this one. So is this giant head and regular cars or tiny cars and regular guy?
Photoshop.
Or Photoshop?
Tiny cars, regular guys.
No, they're tiny cars. These are models. So this guy spends apparently countless hours creating these models. But yeah, it's very, very lifelike, very detailed. This is actually a really funny blog. People who look like money. I think that I've shown you this one, haven't I?
Yeah.
Oh, okay. So now that you know what's going on, somebody explain this to me. It's like
Like Sherlock Holmes.
so we assume that the supports go straight up and down, right? And we assume that this is longer because why? Because it's closer to us. This is longer and in that angle because it's closer to us as well. So in reality, this is in fact shorter. Not just apparently shorter, but it is really shorter. And angled the wrong direction. Yeah. Yeah, so if you know the angles, this is angled less. So balls roll down, it's slower, whereas the other ones angled more and balls roll down, it's faster. All right. So, summary so far. The visual system takes advantage of binocular disparity. Next time, I'm going to steal a bunch of 3D glasses, and I'm going to show you some examples of binocular disparity. The horopter and corresponding points on the retina are used to calculate distance. So if there's a difference between corresponding points, then you assume that something is at a different distance than the horopter. So can anybody define horopter for me? Right, exactly. So it's the depth of focus, basically. It's the plane. It's an imaginary circle around you. It's not exactly circular, but you can think of it as circular. So the plane at which everything is the same distance. And so if everything is the same distance, what is the angular disparity of things on the horopter? Bueller? Bueller? Right, you can say it, Howard. Okay. There is no difference. So that's the definition of the horopter, is that things on the horopter have no angular disparity. Their images fall at the same points on both retinas. And so things that do have angular disparity are off of the horopter. So a positive angular disparity means that it's closer, and negative angular disparity means that it's farther away. We talked a bit about the correspondence problem last time, which is that how do you pick which image on your right eye matches with the image on your left eye. We talked about how perception of an object's size remains relatively constant if you have external cues. And if you manipulate those external cues, then you can come up with some pretty clever illusions. All right, so next time we'll talk about, so these are all sort of 2D or 2I binocular kinds of cues. Next time we'll talk about monocular cues, and we'll do some fun stuff with 3D glasses. And we're done 5 minutes early. How about that?
I have a question.